Hello students, welcome to new lecture on vector analysis. In earlier lecture, we have studied what is vector field, what is scalar field. Also, we have seen differentiation of a vector with scalar quantity. Now we'll see some other aspects of vector analysis. Now in this lecture, we will see infinitesimal angular displacement as a vector. Now let us consider an axis. Now consider a particle which has rotated through an infinitesimal angle. So we will show some path around the axis, and suppose initially particle is at point P and the particle goes from, so its position vector with respect to origin is r. Now we'll see particle goes to point Q from point P. So here angular change is delta theta and it is small. So delta theta, that is angular displacement, is small. Now position vector of point Q is r plus delta r. So we can take this PQ displacement as delta r. PQ displacement as delta r. Now we can have relation between delta r, delta theta and r. Now we can have delta r is equal to delta theta cross r. Delta theta cross r. Then what is direction of this delta theta? Delta theta, it is along the axis. Now, if suppose this change takes place in small time interval delta t, so we can write this as delta r by delta t is equal to delta theta by delta t cross r. And suppose delta t is very small, so I can write delta t tends to 0. So limit delta t tends to 0, delta r by delta t is equal to limit delta t tends to 0, delta theta by delta t cross r. So you can write this as dr by dt is equal to d theta by dt cross r. Now we can write this as dr by dt is equal to omega cross r. Now dr by dt is velocity. So velocity is equal to omega cross r. Now this omega is called angular velocity. And this is direction of angular velocity. Now here we will combine infinitesimal rotations. Consider initially particle is at point P, then it goes to point Q, and then it goes to point R. Here position vector of P is R1, position vector of Q is R2, and position vector of R is R3. And here angular displacement is delta theta 1 between these two, and angular displacement between these two is delta theta 2. Now here we can write R2 is equal R2 is equal to R1 plus delta R1. So this is delta R1 and this is delta theta 1. And we can have delta R1 is equal to delta theta 1 cross R1. So let us call this as equation number 1, this as equation number 2. We can write R3, position vector R3 is equal to R2 plus delta R2. So this one is delta R2, delta R2. So here R3 is equal to R2 plus, we can write this as delta theta 2 cross R2 as the same way as equation 2. So here R3 is equal to, now we know R2 from equation 1, this is R1 plus delta R1 plus delta theta 2 cross R1 plus delta R1, delta R1. Now here we can write R3 as R1 plus, now delta R1 is delta theta 1 cross R1. So delta theta 1 cross R1 plus delta theta 2 cross in bracket R1 cross delta R1. So if we simplify this, we will get R3 is equal to R1 plus delta theta 1 cross R1 plus delta theta 2 cross R1 plus delta theta 2 cross delta R1. Now if we see delta theta 2 cross delta R1, now change is infinitesimal change. So delta theta 2 cross delta R1, we can simply ignore this. Ignore this because of smallness. So we get here R3 is equal to R1 plus, you can take delta theta 1 plus delta theta 2 cross R1. Now see here, so what happens here? We can write position vector of point R in terms of position vector of point P. So here we have combined infinitesimal rotations, that is delta theta 1 plus delta theta 2. Now we will go to components of linear velocity and acceleration in plane polar coordinates. Now we will see components of linear velocity and acceleration in plane polar coordinates. What is need of this? In some situations, the motion of particle or body can be studied conveniently using plane polar coordinates instead of Cartesian coordinates. For example, if we want to study motion of planets around the sun, we know planet is moving around the sun in elliptical orbit, so it is curved path. or motion of electron around the nucleus. In such a situations or in such a examples, the force acting on particle is directed towards a certain point and maybe origin of plane polar coordinates, maybe towards origin of plane polar coordinates. In such a motions, means motion along curved path, we may use plane polar coordinate system. So here I have taken Cartesian coordinate system. It is two-dimensional one. And suppose particle is moving along curved path. We will take point P on the path. So at time t, particle is at point P. Now let us join OP. Means join point P with respect to origin O. Now let us draw perpendicular from point P on x-axis, and that point is Q. Now we can take distance OP as R and angle made by OP with respect to x-axis is theta. Now this R and theta are called polar coordinates. Now here we can take this OQ as x and PQ as y. PQ as y. And this one is perpendicular. So we can write here from triangle OQP, x by r is equal to cos theta and y by r is equal to sin theta. Now r and theta are called polar coordinates. So we can write here x is equal to r cos theta and y is equal to r sin theta. So these are transformation equations. These are called transformation equations. Now, here we can have r. From these two equations we can have r is equal to root of x square plus y square and theta is equal to tan inverse y by x. Tan inverse y by x. These are inverse transformation equations. Now if we talk in terms of vectors, I is unit vector along x-axis, j is unit vector along y-axis, then position vector of point P is r, and we can write that as Ix plus jy. So if we use x and y, we get vector r is equal to I into magnitude r cos theta plus j into magnitude r sin theta. So if r is a position vector of a particle at an instant or at time t, making an angle theta with x-axis, then delta r by delta r represents vector along increasing r, and delta r by delta theta represents vector along increasing theta. Now we can have unit vectors. So I will call unit vector ER is dabba R by dabba R upon its magnitude, and E theta, that is dabba R by dabba theta upon its magnitude. These are two unit vectors. Now what is direction of ER and what is direction of E theta at point P? So if we take unit vector along increasing R, that represents ER, and E theta. E theta, it is tangential to the path at point P. E theta. And ER and E theta are mutually perpendicular to each other. So these are unit vectors, ER and E theta. Now we will find ER and we will find E theta. What is ER? Now, what is dabba R by dabba R? So if we see here, dabba R by dabba R is equal to, now R is this, R is this. So dabba R by dabba R is nothing but I cos theta plus j sin theta. So ER is equal to I cos theta plus j sin theta upon its magnitude. So magnitude is root of cos square theta plus sin square theta. So we get here I cos theta plus j sin theta, because square root of cos square theta plus sin square theta will be equal to 1. So this is ER. Now what is E theta? Now we know dabba R by dabba theta is equal to, dabba R by dabba theta is equal to, we will get minus I R sin theta plus j R cos theta. So E theta will be equal to minus I R sin theta plus j R cos theta divided by square root of R square sin square theta plus R square cos square theta. So we will get E theta is equal to minus I R sin theta plus j R cos theta divided by R. So here E theta will be equal to minus I sin theta plus j cos theta. This is E theta. So we have R is equal to this, and ER is equal to this, and E theta is equal to this. Now we have R is equal to what? R is equal to I R cos theta plus j R sin theta. So I can take R common. So in bracket I cos theta plus j sin theta. So I can write this as R into unit vector ER into unit vector ER. Now differentiate this with respect to time. So I can take dr by dt, and this dr by dt, it is velocity of the particle. So v is equal to, we can take d by dt of r into unit vector ER. So we get this as dr by dt, sorry, we get here dr by dt into ER plus r into der by dt. So I can write v is equal to now. So v is equal to now let us call this dr by dt as r dot. Dr by dt as r dot, that is first order derivative of r with respect to time, into ER plus r into d by dt. So we can write this as d by d theta of ER into d theta by dt, because ER depends on theta only. So I can write this as r dot ER plus r into theta dot, where theta dot is d theta by dt, into d by dt of, now what is ER? That is I cos theta plus j sin theta. So we get velocity v is equal to r dot ER plus r theta dot into d by dt of I cos theta, we will get minus I sin theta plus j cos theta. Now we know minus I sin theta plus j cos theta, it is e theta. So we get here v is equal to r dot ER plus r theta dot e theta. E theta. So here we call this as v is equal to vr vector plus v theta vector. Now vr, it is r dot er, that is called radial component of velocity. So this vr, it is radial component, and this is angular component. Angular component. So vr is r dot into. So magnitude of vr is r dot. Magnitude of e theta is r theta. So this is about linear velocity in plane polar coordinates. Now we will see acceleration. Now we have seen v is equal to r dot er plus r theta dot into e theta. Now we will take derivative. So dv by dt, and this dv by dt is acceleration. So acceleration of the particle is equal to r dot, so d by dt of r dot er plus r theta dot e theta. So we can write here d r dot by dt into er plus r dot into d by dt of er plus d by dt of, from this term, r into theta dot e theta plus r d theta dot by dt into e theta plus r theta dot into d by dt of e theta. Now here, this first term dr dot by dt, we can take this as second order derivative of r with respect to t. So let us call this as r double dot into er plus r dot. Now I can write this as d by d theta of er into d theta by dt plus now dr by dt we can write this as r dot theta dot into e theta plus r. Now this term d by dt of theta dot we can write this as theta double dot e theta plus now r theta dot. Now here d by d theta of e theta into d theta by dt. So we get here r double dot er plus r dot theta dot into d by d theta of er plus r dot theta dot into e theta plus r theta double dot plus r theta dot square, because this term will take as theta dot, this theta dot into this theta dot, that is theta dot square, d by dt d by d theta of e theta. So this is acceleration. Now we will find d by d theta of er, that is d by d theta of I cos theta plus j sin theta, and this comes out to be minus I sin theta plus j cos theta. So this is e theta, this is e theta. And what is d by d theta of e theta? So it is d by d theta of e theta means minus I sin theta plus j cos theta. So we get here d by d theta of sin theta, that is cos theta. So minus I cos theta, and d by d theta of cos theta is minus sin theta. So minus j sin theta. So we can take minus sign out. So minus in bracket I cos theta plus j sin theta. So this is minus er, minus er. So what is acceleration? So acceleration is a is equal to now r double dot er, this term. Now r theta dot and d by d theta of er is e theta. So we get here plus r dot theta dot into e theta plus r dot theta dot into e theta. So I can write this as 2 times plus r theta double dot. Sorry, here there is e theta also. E theta plus r theta dot square into d by d theta of e theta, that is minus er. So I have taken minus sign here. So a is equal to r double dot minus r theta dot square into er plus r theta double dot plus 2 r dot theta dot into E theta. So this is acceleration in plane polar coordinates. Now this first term, it is radial component and this one is angular component. So we can have AR radial component is equal to R double dot minus R theta dot square into ER. So magnitude AR is R double dot minus R theta dot square. And angular component, it is R theta double dot minus plus 2 R dot theta dot multiplied by E theta. And now the resultant acceleration, it is directed towards some center. It is directed towards some center. So the force is called central force. The force is called central force. So what happens here? So when suppose we take here Cartesian coordinate system and if particle is moving along curved path, so at point P, this is ER, this is E theta, because this angle is theta, this is position vector R. So corresponding acceleration, it is directed towards some center like this. So that may be somewhere here or that may be towards center of Cartesian coordinate system. So the force we get in this case, it is central force. Central force. So here acceleration is directed towards some point. So this is about linear velocity and acceleration in plane polar coordinates. So thanks about this. Now in next lecture, we will study gradient of a scalar field. So thanks very much again.